Hey, you ever just, stare off into space? Like, really
Yeah.
think about what's out there, or even just what's here.
Uh-huh.
It's kind of mind-blowing when you stop and think that all of this, I mean, your phone, your coffee mug, the entire planet, they had to come from somewhere, right?
It's a fundamental
And
question.
the bonkers question is, could it have just popped into existence from, like, absolutely nothing?
That's the kind of deep, um, fundamental question that cosmologists, wrestle with constantly. And while there isn't a simple yes or no answer,
Right.
the inflationary universe theory gives us a really compelling way to think about those first incredibly tiny moments of existence.
Inflationary universe theory.
Mm-hmm.
Okay, sounds a bit sci-fi. But our mission today for this deep dive is to try and get our heads around it. We're using Alan Guth's book, The Inflationary Universe, as our guide. We want to understand the core ideas, What problems was inflation trying to solve? How does it even work?
And what evidence does Guth present?
Exactly. His book is, well, it's a landmark. It gives us the science, but also the personal story behind this really revolutionary idea.
So we're pulling out the key concepts. Got it.
Yeah, to give you a solid grasp on why inflation became, such a big deal in cosmology.
Okay, let's dive in then. So before inflation, the main idea was the hot Big Bang theory.
That's right. It's still a core part of the picture, really. Inflation builds on it, doesn't replace it entirely.
Right. The universe starting super hot, super dense, and just expanding. But Guth points out that original picture, it had some serious puzzles, some head scratchers.
It did, yeah. A lot was explained, but some really big questions were left hanging. One of the biggest was just how incredibly flat the universe seems to be.
Flat, you mean like geometrically?
Exactly. Think about the universe expanding, but gravity is always pulling it back, trying to slow it down.
Now, whether the universe expands forever or eventually collapses back or just sort of coasts, that depends critically on how much stuff, how much mass density there is. We call that value omega.
Omega. Okay, the
Yeah.
cosmic density factor.
Light chuckle, something like that. And the thing is, for the universe to be as flat as we measure it today, after billions of years,
Yeah.
it means that back near the very beginning, its density had to be unbelievably close to this critical value where it's perfectly balanced. Guth uses this great analogy from Robert Dick.
Oh, yeah.
Imagine trying to balance a pencil perfectly on its sharp point.
Oh, right. Totally unstable. The slightest nudge and it falls over.
Precisely. If omega was exactly one perfectly balanced, it should stay that way. But if it was off by even the tiniest fraction,
It would have veered off massively by now.
hugely. For it to be anywhere near flat today, Guth mentions it needed to be accurate to like 1 part in 10 to the 15, that's a quadrillion, just 1 second after the Big Bang.
1 part in a quadrillion. Wow. That feels really improbable, like cosmically lucky.
It does seem that way, doesn't it? It demands this extraordinary initial fine-tuning. That's the flatness problem. And that wasn't the only puzzle.
There was more.
Oh, yeah. Particle physics theories from that time, specifically these grand unified theories, or GUTs.
Trying to link up the fundamental forces, right?
Exactly. They predicted the existence of these, well, really exotic particles called magnetic monopoles.
Magnetic monopoles, like a North Pole all by itself, without a South Pole.
That's the idea. Very strange. And the calculations showed the early universe should have produced just tons of them, an absolute flood.
So where are they? Don't tell me my compass is broken.
Chuckles. Well, we've never definitively found one. The universe should be swimming in them, according to those theories, but nothing. That's the magnetic monopole problem.
Okay, so the standard Big Bang had this flatness problem needing this crazy precision and this monopole problem predicting stuff we don't see. Then Alan Guth has this, what did you call it? A spectacular realization.
Yes. His big insight came from thinking about phase transitions in the super early universe, like water turning into ice, but, for the fundamental forces.
Yeah.
He considered the possibility that the universe could have gotten stuck in a high-energy state during one of these transitions, sort of like supercooled water that stays liquid below
There's
freezing.
a super-cooled universe. Okay, how does that help?
Well, this supercooled state is what's called a false vacuum. And a
Hmm.
false vacuum has this really weird property. It has a constant energy density even as space expands.
Constant energy density.
hmm And that leads to something even weirder.
Ah.
Negative pressure. That's like anti-gravity. Almost. Instead of gravity pulling things together, this negative pressure actively pushes everything apart.
Negative
Violently.
pressure. So the universe suddenly hits the accelerator, like really hard.
Exactly. It would cause the universe to expand exponentially, just
Yeah.
ballooning outwards at an unbelievable rate. Guth mentions a doubling time of something like 10 to the minus 37 seconds. Ridiculously fast. He uses that old legend, the king and the chessboard with the grains of rice.
Ah, the exponential growth thing.
Yeah.
1 grain, then 2, then 4. Ends up being an insane amount.
Precisely. That's the kind of growth we're talking about. And this incredible burst of expansion inflation does two crucial things.
Okay.
First, it stretches the fabric of space-time so much that any initial curvature gets completely flattened out,
Right.
inflating a very wrinkly balloon until the surface looks perfectly smooth, solves the flatness problem.
Ah, okay. It just irons everything out. And the monopoles.
The same expansion dilutes them massively. They get spread so incredibly thin that the chances of finding one in our observable universe become practically zero. Sweeps them under the cosmic rug, basically.
Okay, that actually sounds pretty neat. It solves both big problems with one mechanism. But was it perfect? Any hitches?
Yeah, the original version, what Guth first proposed, had a significant issue called the graceful exit problem.
Graceful exit. Sounds like leaving a bad party.
Apples. Sort of. The false vacuum had to decay eventually, right? Transition into the normal, slower expanding universe we live in, full of matter and radiation.
Makes sense.
But Guth's original model predicted this decay would happen in a really messy, uneven way, like bubbles of the new vacuum forming and violently colliding. It would leave the universe incredibly clumpy and inhomogeneous, not like what we see.
Right, we see large structures, but it's pretty smooth on the biggest scales. So giant cosmic crashes weren't the answer. What happened then?
Well, the idea wasn't abandoned. People realized how powerful it was. Andre Lind, and independently Andreas Albrecht and Paul Steinhardt, came up with refinements, often called new inflation.
New and improved inflation.
Basically, yeah. In these models, the idea is that our entire observable universe grew out of just one tiny region, one bubble, that inflated enormously.
So we're inside one smooth, successful bubble, avoids the messy collisions.
Exactly. It makes the exit much more graceful. And this new inflation also introduced the idea of a specific field driving the process.
Ah, you mentioned this earlier, the inflaton field.
That's the one. A hypothetical scalar field different from the Higgs field known from particle physics. The key thing about the inflaton is that its energy potential, its landscape, needed to be incredibly flat.
Flat landscape, meaning?
Imagine a ball rolling down a hill. If the hill is steep, it rolls fast. If it's almost flat, a very gentle slope, the ball rolls very slowly.
Okay.
The inflaton field is like that ball rolling down a very, very gentle slope. As it slowly rolls, its energy drives the massive exponential expansion. That slow roll is crucial for inflation to last long enough and work properly.
So a new field, not the Higgs, with this special flat potential. Did this new version make testable predictions?
Yes, definitely. One of the key predictions relates to the origin of cosmic structure galaxies, clusters of galaxies.
Where did the initial seeds for those come from?
Inflation predicts they came from tiny quantum fluctuations, little jitters in the inflaton field itself during that exponential expansion. Inflation stretched these microscopic quantum fluctuations to enormous astronomical scales.
Wow, quantum effects becoming galaxy-sized.
Essentially, yes. And calculations show that this process should create a specific pattern of density variations, what's called a scale invariant spectrum. Basically, the fluctuations look statistically similar on all different size scales.
And is that what we see?
Well, that prediction actually matched earlier ideas about what kind of fluctuations would lead to the universe we observe, which was encouraging. But there was a catch initially.
Oh.
When they plugged in the numbers using standard grand unified theories for the inflaton field, the magnitude of the predicted fluctuations was way too big. It would have made the universe far too lumpy compared to what we observe.
Ah. So the pattern was right, but the strength was wrong.
Precisely. Which again pointed towards the inflaton needing to be something different, maybe not directly tied to those GUTs, something with that required ultra-flat potential.
Okay, so inflation seems like a really powerful idea, solving big problems, making predictions. But it also introduces its own complexities, like needing this special inflaton field. What about actual observational evidence? You mentioned Guth talks about the CMB.
Absolutely. The cosmic microwave background radiation, its discovery by Penzias and Wilson back in the 60s was, well, monumental. It was the afterglow of the hot Big Bang itself.
The universe's baby picture.
Exactly. Coming from about 380,000 years after the start, it showed the universe really was hot and dense early on, providing the foundation inflation builds upon. Guth mentions Dick's group at Princeton was right on the verge of finding it, too.
And later, satellites got a much closer look at that baby picture, right? Like Kobe.
Yes. The Kobe satellite in the early 90s was huge. It measured the CMB's temperature across the whole sky with incredible precision and found exactly what theories were predicting. Tiny variations in temperature from spot to spot, anisotropies.
The wrinkles in time, basically.
That's the popular phrase, yeah. These tiny temperature differences, maybe 1 part in 100,000, were the imprint of those slightly denser and less dense regions in the early universe, the seeds of structure.
And did the pattern match inflation's prediction?
The scale invariant prediction from inflation was beautifully consistent with what Kobe saw. Now, other theories, like cosmic strings, were also sort of compatible at first. But later, more precise measurements, like from the WMAP and Planck satellites, have really strengthened the case for inflation and ruled out many alternatives. The specific pattern of those hot and cold spots fits the simplest inflationary models remarkably well.
So the CMB map is like exhibit A for inflation.
It's incredibly strong evidence, yes.
Huh.
And don't forget the flatness problem we started with.
Right, the pencil balancing act.
All our best measurements continue to show the universe is extremely close to flat. Omega is very, very near to 1.
Which inflation naturally explains through that stretching.
Exactly. Without inflation, that flatness requires that absurd fine-tuning at the beginning. With inflation, it's a natural consequence of the exponential expansion. Guth really hammers home just how precise things needed to be without inflation.
It really does sound like inflation solves a lot. But you mentioned Guth also touches on ongoing questions, like an age crisis.
Yeah, that was an issue, particularly around the time the book was written, though it's somewhat less acute now with better data.
Yeah.
The problem was a potential mismatch.
Okay.
Astronomers measure the universe's expansion rate, the Hubble constant, to estimate the universe's age. And they also estimate the ages of the oldest things in the universe, like globular star clusters.
Did the numbers not line up?
For a while, some measurements of the Hubble constant suggested the universe might be younger than the oldest stars it contained, which is, impossible.
Yeah, that's a bit of a paradox. An older star in a younger universe.
Right. Guth mentions this might hint that our standard cosmological model needed further refinement. Maybe the universe isn't perfectly flat, but slightly open. Or perhaps we need a cosmological constant. Einstein's biggest blunder, which we now call dark energy.
Dark energy. That's a whole other deep dive.
It is. But it shows cosmology is still evolving. Inflation is a cornerstone, but the complete picture might still have twists.
Okay, so we've covered the why and how of inflation, the evidence. But what about the absolute beginning, before inflation? Where did even the potential for inflation come from? Guth goes there too, right? Into the really speculative stuff.
He does, and it gets pretty mind-bending. He discusses Edward Tryon's idea from the 70s. Maybe the whole universe is just a quantum fluctuation.
Like it borrowed energy from nothingness for a bit.
Sort of. Quantum mechanics allows for these temporary fluctuations, energy popping into existence briefly. Tryon suggested, what if the universe is just a really, really big, long-lived one?
Wow, a universe popping up like a particle-antiparticle pair.
That was the analogy. But, as Guth notes, it didn't fully explain why it would then expand and become so large and structured. Then there's Alexander Vilenkin's even more radical idea.
More radical than appearing from a fluctuation.
Yeah, quantum creation from literally nothing. Not just empty space, but the absence of space, time, matter, everything.
Nothing. My brain hurts.
Chuckles. It's definitely abstract.
Like,
Guth also mentions the Hartle-Hawking no-boundary proposal. It's a mathematical approach suggesting space-time might not have a definite starting edge or boundary in the quantum realm. Time itself might emerge.
so the laws of physics themselves might allow or even require a universe to begin.
That's the direction these ideas explore. It's highly theoretical, on the edge of physics and philosophy, really.
And what about creating new universes, pocket universes?
Yes. That comes from the idea of internal inflation. If inflation involves this false vacuum state, maybe it doesn't end everywhere at once. Maybe space is constantly inflating overall. But in some regions, the false vacuum decays, forming a bubble universe like ours. Meanwhile, the space between these bubbles keeps inflating, potentially spawning more bubbles eternally.
So our universe could be just one bubble in an infinite cosmic ocean, a multiverse.
It's a possibility that arises quite naturally from some inflationary models. Guth mentions calculations suggest the probability of us creating a new universe, say in a lab, is incredibly tiny. But in an eternally inflating cosmos, maybe it happens.
Makes you feel small. And you mentioned something about negative energy and gravity being key to this creation from nothing business.
That's a really crucial concept. The idea is that the total energy of the universe might actually be zero.
Zero. But look at all the stars, galaxies, all that matters energy, right? EMC squared.
It is. That's a huge amount of positive energy. But gravity, the gravitational field itself, can be thought of as having negative energy.
Negative energy, how does that work?
Think about pulling two objects apart against gravity. You have to add energy. So the bound state, when they're together, has less energy or negative potential energy relative to being infinitely far apart. The gravitational binding energy of the whole universe could be a large negative number.
And that negative energy could perfectly balance out all the positive energy of matter and radiation.
Exactly. If the total energy is zero, then creating a universe from nothing doesn't actually violate energy conservation. You're creating both the positive and negative bits simultaneously, netting out at zero.
A zero-energy universe emerging from nothingness via quantum rules, driven by inflation, that is.
Wow. It's a stunning picture, isn't it? So, recapping our deep dive into Guth's work, inflation elegantly solves major puzzles like flatness and monopoles left by the standard Big Bang.
Right.
It makes predictions, especially about the CMB, that have been remarkably confirmed by observation. It links the incredibly small quantum physics particle fields to the unimaginably large the entire cosmos. And it opens doors to thinking about the ultimate origin, maybe even from nothing.
Incredible stuff. It leaves you wondering, if our universe really did expand from this tiny speck of false vacuum, what does that imply about reality itself and this idea of other universes?
It definitely stretches the mind.
It seems the quest to understand our cosmic origins is far from over. Inflation is a huge piece of the puzzle, a fascinating chapter, but maybe not the final word. Thanks for joining us on this deep dive.
Always a pleasure.
Until next time, keep pondering those big questions.